Good evening, viewers of Acti.com, by Vetri from Pondicherry. Last class, I was discussing what is configuration, what are the types of configuration. Under the configuration, I have discussed what are the methods available for projections to draw structures by viewing a model. Under this, I have discussed three projections. One is Fisher projection, number 2 Newman projection, and 3 Sahar projection. I have explained with the model as well as board, Fisher projection as well as Newman projection. Today, I am going to discuss Sahar projection again by model as well as board. So kindly view and listen carefully. Okay. So what is Sahar projection? In order to convert Fisher projection into Sahar projection, the bottom chiral center is written at front. This is the most important information. Written at the front and the top one at the rear, while the substituents are placed in front and behind as implied in the Fisher projection. So this is the Sahar projection. Let me repeat again. In order to convert Fisher projection into Sahar projection, the bottom chiral center is written at the front. This is the most important. The top one at the rear, well, that is the bottom chiral center written at the front and the top one at the rear, while the substituents are placed as in the case of Fisher projection, left and right. So this is the important. Okay, let me go for a suitable example I will take. So what you are seeing now, it is the structure of D-erythrose. So in this D-erythro, there are 4 carbon atoms, carbon 1, carbon 2, carbon 3 and carbon 4. So if you view this structure, that is D-erythrose by Fisher, as usual, so now what will happen? This CHO, the second carbon atom CHOH, H and OH, third carbon atom H and OH, and fourth carbon atom CS2OH, they are lying in vertical position. Whereas, in the second carbon atom H and OH, in the third carbon atom H and OH, they are lying in the horizontal position pointing toward the observer. This is according to Fisher projection. Okay, so this Fisher projection, how to convert into Newman as well as Sahars. Here, Newman to Sahars I have written. So I will show you both. That is from Fisher to Newman as well as Sahars I will show you. Now, kindly see the model. So, according to, that is D-erythro, kindly see the structure here, D-erythro structure. This is Fisher projection. So these 4 carbon atoms, CHO, that is 1, 2, 3 and 4th carbon atom, they are lying in the vertical positions, whereas this H in the second, this OH in the horizontal, this H and this OH in the again horizontal position pointing toward the observer. So now I will show this model, D-erythrose model. Just see, this is the model. If I am showing the model, suppose you are observing, it's a students, you are observing, that is, this is carbon 1, kindly follow, this is carbon 1, CHO, COH, CHO, aldehyde group. This is carbon 2, carbon 3 and carbon 4, CH2OH. Let me repeat again, CHO, carbon 1, CHOH, carbon 2, CHOH, carbon 3 and CH2OH, carbon 4. So, when we are viewing from there, kindly see at this, that is this CHO, C2, C3 and C4, they are lying in the vertical positions. Whereas, this hydrogen in the second carbon atom, this OH And the third carbon atom, this hydrogen and this OH lying again in the horizontal position pointing toward the observer. So when we are doing this model by Fisher, CHO and CH2OH, top CHO and bottom CH2OH moving away from the observer, away from you. Whereas this second carbon atom H and OH, this H and OH moving towards you. This is the method of viewing the model. And we are representing in two-dimensional board or notebook. Right. So this is the way we have to view that is Fisher projection. Okay. The next question arises, how to view the Newman projection? There are two ways I can view. That is, kindly see here the board. One is, I can view from here, that is from CHO I can view. In that case, I can say this is 1, 2, 3 and 4 carbon atom. So 2 and 3 I will consider. So 2 will be considered as a point and 3 will be considered as a circle. When you view from the carbon, the other side, CHO, so CHO will be very near to you. So automatically C2 carbon will be a point and C3 carbon will be a circle. The other way, suppose if you are viewing from here at the bottom, again the model, I am showing you two-dimensional itself, you can understand, I will show the model. If you are viewing from this, automatically now C4 carbon atom will be very near to you. So as well now, kindly follow, this is C3, C3 will be a point and C2 will be a circle. So you must understand this. What way we are going to view the model by, that is the Newman projection. I will show you the both way you can understand. The first method is, kindly follow, this is the Fisher projection. Now I am going to show how to view according to Newman. Suppose I am just rotating, just here. This is the way. That means, this is CHO, it is very near to you. This is carbon 1, this is carbon 2, carbon 3 and carbon 4 is this CH2OH. So C2 carbon according to you, it is the point. We are very near to you, it is a point. And C3 is just backside to, it is a circle. So now we are being like this is an eclipse form. CHO and CH2OH facing each other. So this is an eclipse form. So this eclipse form, I can now by rotating the circle, that is the carbon, C3 carbon, that is circle, you can get 6 conformation possible. Kindly see, this is number 1, eclipse, fully eclipsed. Now I am rotating clockwise. This is staggered, partial staggered. Number 2, again eclipse. Number 3, staggered. Number 4, this is the anti, CHO, CHOH opposite to each other. Anti, number 4. Then number 5, eclipse. And then number 6, again, that is number 6, this is again staggered. So there are 6 conformations, this is original. So this is the way we have to view. That is, if you view C2 is nearer to you by viewing C2 as a point and C3 as a circle, this is the structural view for the Newman projection. The next question, but the other way, suppose see here, this is original, kindly follow me again. This is original Fisher projections. So previously I have shown you, if you view like this, this is the one way. Now this is again the Fisher projections. Now I am going to see the other way, just see, I am now keeping like this. This is the other way of looking the Newman projection. Now in this case, just see, now the carbon 1 here, it is CHO here, CH2, this is number 2, number 3, number 4. So number 4 is now nearer to you. According to, that is Sagar projection, we have to view such a way, that is, this one should be nearer. Okay. This is what I am saying, only Newman, kindly remember. So C4, this is C3. The interesting, important information is, C3 is very near to you, that is considered as a point. So automatically C2 will be away from the view, so it will be a circle. So C3 is a point, C2 is a circle. So by keeping like this, again I can give 6 possible ways of spatial configuration. This is eclipse, fully eclipsed. So kindly see, CS2OH is very near to you, that is backside CHO facing each other, eclipse. So I am going to rotate again clockwise, you will get 6 confirmation. Kindly follow me. So this is fully eclipsed. So I am going to rotate clockwise. Remember, I am going to rotate clockwise. So when I am rotating, so this is number 2. First one, eclipse number 1. This is staggered number 2. Then eclipse number 3. Again staggered number 4. Opposite. CHO, CH2H 4. Then eclipse 5. Staggered 6. And original. This is the 6th confirmation possible. Always out of 6, 3 eclipse confirmation, 3 staggered confirmation. We know only staggered is more stable than eclipse. Out of 3 staggered, 1 is more stable. That will be when CS3 and CS2OH groups, CHO group and CS2OH group, if they are 180 degree away, then it is called anti-confirmation. So let me repeat again, that this is the only I am going to use for to convert it into Sahar. So kindly see this. Let me repeat again. This is the original eclipsed form. Kindly follow. This is Fisher, the corresponding. That is, as per the rule, we have to see. This is the way we have to see according to the Fisher. On your right OH, left H, on your right OH, H. So CHO, CH2O. This is the Fisher. So what I am now bringing like this, so this is bringing in here, so CS2O is coming nearer. So C3 is a point, C2 is a circle, this is eclipse. Number 1, let me repeat again. Number 1, staggered. Number 2, staggered. Number 3, eclipse. Number 4, staggered. Number 5, eclipse. Number 6, staggered, original. So this is the way we have to view the model. Now, so this Newman projections, now I am going to show how this we have to represent in Sahar projection, then it will be easy for you. Kindly follow me. So kindly look at the board now. So this is I have written, this is the Fisher projection, this is number 1, number 2, number 3, number 4. So what here I am representing here, I am going to convert first Newman as well as Sahars. In Sahars, the idea here it is conventionally, we are viewing from this is the convention we have to. So as per the Sahar projection, the 4th carbon, that is 4th, it should be very nearer, that means in front of the viewer. So third carbon will be a point and 2 will be a circle we have to view in this case. So automatically in Newman projection, so I have already shown you, this is the Newman projection. Kindly follow me. And you kindly see that the first case point, we are saying the point, that is here C3 is the point, on your right OH and your left H, and this is the below is S2OH, and next the away from the circle, again OH on the right, H is on the left, CHO. This is the eclipsed form of Newman projection. So kindly see the board. So this eclipsed form, so I am going to convert into Sahars. I have shown here. It is Sahars. What way? So only thing is, the 3rd carbon atom point I am not going to rotate. The 3rd carbon I am not going to, that is 3rd carbon means this is the 3rd carbon. I am not going to rotate because we are considering a point. So what we are going to rotate is, we are going to rotate only circle. So this is I am going to rotate in clockwise. So kindly see structure 1. This is structure 1. Kindly follow. This is the eclipsed form of Newman. So in the Sahars, what behavior have to kindly see, this is the most important information. In Newman projection, we cannot see the bond, carbon-carbon bond we cannot see. Between C2, that is C3 and C2, we cannot see. In the Newman projection, we cannot see because we are seeing is a point, backside is a circle, so we cannot be able to see. But in the case of the correspondingly, what you can call it as the Sahar projection, we have to see like this. Actually, this is on your right, this is on left, automatically. So now this carbon-carbon bond you can see. Kindly see. This bond you can see. Kindly follow. So I think here, so we are in the board. Now you are seeing like this. We are seeing from here. From here you are seeing. In that case, on your left is H, on your right is OH, below is CH2O group. This is actually carbon 1, carbon 2, carbon 3 and carbon 4. Carbon 3 is a point we are not going to rotate. What we are rotating is only carbon 2 you are rotating because it is a circle. Kindly see, I am going to rotate. This is structure 1. So according to, this is Newman structure 1. Now just see, this is the correspondingly the Sahar structure 1. See at the right side, Sahar structure 1. Kindly look at this. Look at the board now. This is the Sahar structure 1. The information is, now let me go for the next one. Structure 2. Now just see, I am going to rotate now. So now structure 3 Newman is, so I am going to now rotate clockwise. I am getting a staggered confirmation. First one is the eclipse, this is the staggered. Kindly follow me. This is staggered confirmation. So automatically you can see that is CHO opposite OH, OH opposite again H, and CS2 opposite H. This is the staggered confirmation for Newman. So how to view now? Now we view, this is the corresponding Sahars. So as usual, the C3 carbon is nearer, so we are rotating only C2 carbon. This is the way you have to see. This is carbon-carbon bond you are seeing. Now this is the model. Now go to the board now. So this is I am not rotating. C2 that is the C3 I am not rotating. C2 only I am rotating. So now it is, kindly see, this is the corresponding the staggered form. Staggered means you can see here opposite, that is the staggered form I have already many times I explained you with the ethane, propane and butane. This is the corresponding staggered form. This is the corresponding Sahar. This is structure 2. Okay, I will rotate now. I will go for structure 3. This is structure 3. Okay, how to view this? This is the corresponding Sahar projection. So this carbon, it is a point, it is not rotating. We have rotated only the C2. So now automatically you can see on your left is CHO, on your right is H, and below it is that correspondingly that is OH. So this is the way we can view that. This is the structure 4, CHO and CS2OH, it is facing opposite side, OH and OH opposite, H and H opposite. This is structure 4. As usual, so now how to view this? You can view like this. If you view like this, so in your nearer, again, on your left, actually it is there, H, on your right, OH, below CH2, it is not changing at all, always. So only change is here. Just see, at the top CHO, on your left, again, OH, on your right, see this board here, this is not changing. So here it is, top CHO, on your left, OH, on your right is H. Whatever you are seeing in the model, you can see here. So what is simply, we are just taking and putting in this. Only thing is same model, instead of when we are doing a Newman projection, we are not seeing the carbon-carbon bond. But when you are seeing the Sahar projection, we are seeing we have to view the model such a way that carbon-carbon bond we have to see. Okay, let me go for the structure 5. So structure 5, let me show you now. So I am going to rotate again. So when I am rotating clockwise again, so kindly this is an eclipse. In the eclipse, again as usual, the OH and the CHO facing each other, the H and OH facing each other, and H and CS2OH facing each other. And see the board now, that is H and OH and CHO facing each other, OH and H facing each other, H and CHO facing each other. That is what you are seeing here. Just see the model. Okay, now how to view this? Again, as usual, view the according to Sahar. Simply, so now you are seeing this carbon-carbon bond length. You are seeing. So this is very nearer, this is far away. So in that case, just see here, automatically on your left, here is OH, on your right it is CHO, and below it is H. Kindly look at here. So below H, on your left OH, on your right is CHO. So this is the automatically eclipsed form of Sahar projection. This is the Sahar's eclipsed form. Let me go for the next one. The sixth structure. So now I am going to rotate again. So now just see here, in this case again, so OH and CS2OH opposite, CHO, H opposite, H and OH opposite. This is the staggered confirmation. This is the corresponding Newman staggered. So corresponding Sahars, just see here. So automatically you can see OH in the carbon, that is the second carbon above the plane, and then on your left is H, on your right is CHO. This is the structure. So come to the board now, and that is when you are viewing from here, top is OH automatically, and your left is CH and your right is CHO. So this is the way we have to view the Sagar's projection. So totally we are having the 6 possible structures as in the case of Newman and Sagar's. So out of 6 we know already staggered will be more stable than that is eclipse. Out of 3 staggered, so only in that is structure I will show you which is more stable. I will show you now. Opposite side it will be staggered. Kindly follow me. Now this is the number 4. This is the more stable. More stable because this is called anti-conformation. So CH2OH group and CHO group, it is opposite, 180 degree away from each other. So that is the most stable. And here also you can just see in Newman, it is also more stable. So this is the way we can convert now directly. Let me repeat again. What is the important information here? So when we are converting Fisher projection into Sagar's, so what we have to do now? That is, what we have to do now, so we have to view such a way, now that is the third carbon, this is the lowermost asymmetric, in this case it is the third carbon atom should be viewed as a point, and second carbon atom should be viewed as a circle. This is the important information. And we are keeping this is 1, this is 2, this is 3, this is 4. And we are not rotating C3 carbon, we are rotating only C2 carbon. So when we are rotating, we are getting 6 different configuration. One is 3 eclipse and 3 staggered. And only staggered is most stable, I have already explained. Out of 3 staggered, the most stable is when CH2OH group and CHO group are 180 degree away, that is most stable. So this is the way we have to view the formula, that is Sagar's projection. So that is regarding for the conversion of Sagar's formula. That is Fisher to Newman and Newman to Sagar's. This is very, very easy. So once if your predictors Newman, conversion will be very, very easy. You can. Okay, let me go for the next. Now, so now we know how to project a three-dimensional molecule into 2-dimensional board or notebook. We can. We have that is 3. One is Fisher. Number 2, Newman. Third is Sagar's. I have already pointed out, Fisher we are using to write the structure in 2-dimensional board or notebook, whereas Newman and Sagar's we are using only to predict the stability and study the stereochemistry, reactivity, etc. Okay, now, what are the system of configuration in organic chemistry we have to study? There are 2 or 3 important system of configuration we are interested. One is D and L system of configuration, 1. Number 2, R and S system of configuration, and number 3, E and Z system of configuration. So these 3 configurations we have to discuss under the configuration. Number 1, D and L system of configuration. Number 2, R and S system of configuration, and number 3, E and Z system of configuration. Let me discuss one by one. Let me take first one, D and L system of configuration. What is the DL? The D and L system of configuration was used in olden days and the lowermost asymmetric carbon atom of an optically active compound. This is the most important. Lowermost asymmetric carbon atom of an optically active compound. So whenever you want to give common name, so the lowermost asymmetric atom is considered, and based on that the configuration is given whether D or the L. So let me explain. So in the projection formula specified, the carbon chain should be vertical. This is as in the Fisher projection. The carbon chain, because easily oxidizable carbon atom at the top and less easily oxidized carbon atom at the bottom. By keeping this, we have to write the structure vertically. So all the carbon atom in the vertical chain, and the substituents at the horizontal with the asymmetric carbon at the center. So keeping asymmetric carbon center, we are writing the horizontal H and OH or any groups, left and right we are writing. So this is the way we have to project as in the case of Fisher projection. Okay, now in the horizontal positions, if the substituent, any substituent, let me represent X, the X may be a more electronegative atom or group. X may be an atom, more electronegative atom or group, occupies the right hand side of the asymmetric carbon atom, if any electronegative atom or group, that is X, if occupies the right hand side of the asymmetric carbon atom, so we have to assign the configuration is D. It is D. Instead of that, and if the substituent, that is more electronegative atom or group X, occupies the left hand side of the asymmetric carbon atom which is present in the chain, then the configuration is specified as L. So this is the most important information. So D we have to apply where X is present on the right hand side in the lowermost asymmetric carbon atom. We have to assign as L, capital L, if the asymmetric, that if the electronegative atom or group on the left hand side. So let me explain with a suitable example, you can understand. Now I am giving two different examples. So here it is, I am giving as a D class. Why I am giving a D class allele, you can see here. Carbon 1, carbon 2, carbon 3 carbon atom. In this, the central carbon is asymmetric. Why it is asymmetric? Because OH, CHO, H, CH2OH, 4 different. We have discussed already under the optical isomerism. If they are 4 different asymmetric carbon, if it is asymmetric, it will show optical activity. So now in this case, there are two things. So this, why I am calling it as a D? Because as per the D and S system of configuration, so all carbon atom in the vertical chain, CHO, CHOH and CH vertical chain, whereas H on the left, OH on the right, OH more electronegative atom is oxygen. So OH is a group containing more electronegative. Since it is present on the right hand side, I am using D. So its name is, it's a glyceraldehyde. So I am giving the configuration as D-glyceraldehyde. Automatically, the corresponding left hand side, now OH is present on the left hand side. So I am now using as L-glyceraldehyde. So the left side structure I am calling it as a D-glyceraldehyde and right side structure I am calling it as L-glyceraldehyde based on this DL system of configuration. Let me repeat again. That is, when we are giving configuration D or L system configuration to any molecule containing optical active center, so we have to consider lowermost asymmetric center. In the lowermost asymmetric center, if any electronegative atom or group is occupied on the right hand side, assign D, capital D. If any electronegative atom or group it is present in the left hand side, we have to assign L configuration. So in this case, D-glyceraldehyde and L-glyceraldehyde. Let me take another example. So here I am using tartaric acid. I have taken a specific example. Tartaric acid, you know the formula. That is, here it is your structure formula. That is COH, CHOH and CHOH and COH. That is the formula. So I have written two possible ways here. In this case I have shown now. So one case, this is carbon 1, carbon 2, carbon 3, carbon 4. There are two asymmetric centerities there. Same way here again, 1, 2, 3, 4. That is again 4 carbon atoms. So again 2 asymmetric centers there. Kindly follow me, but they are not same, they are different. So now there are 2 asymmetric centers. As per the rule, I have to consider only the lowermost asymmetric carbon atom. The same way here also, lowermost asymmetric carbon atom. So left hand side, now I am using D because OH is on the right side. More electronegative atom O along with H is present on the right hand side, whereas here it is present on the left hand side. I am using L. So this optically active tartaric acid, optically active tartaric acid, I am giving left side structure, I will call it as D-tartaric acid. Right side structure, I will call it as L-tartaric acid. That is, I will call it as structure 1, D-tartaric acid, structure 2, L-tartaric acid. I am calling. So this is the important information. So the reason I have already pointed out. Let me go to the next. Another specific example. Okay. So this is a complicated structure. Kindly follow me. This is a complicated structure. So here C6 H12O6. That is a formula. That is compound having C6H12O6 formula. And in this formula, now if you want to write a possible structure, we can write nearly. That is based on formula. This molecule is containing 4 asymmetric center. 4 asymmetric center. So it's 2 to the power of n formula if you apply. So automatically 16 isomer possible for this. A compound having molecular formula C6H12O6 will have 16 isomer possible. Out of 16 isomer possible for the compound, there will be 8 D form and 8 L form. Kindly follow. This is the most important. Even though it is a complicated, kindly follow. So that is a compound having a formula CCH12O6. It is containing 4 asymmetric center. It is an unsymmetrical. If it is an unsymmetrical, we know the formula 2 to the power of n. So n equal to 4, apply 2 to the power of 4 means we are getting 16 isomer. So if you write all the 16 possible isomers, we are getting correspondingly 8 D form and 8 L form. So that means here, just see here, I am showing here there is one of the 16 isomer is D-glucose we are calling. One of the 16 isomers we are calling is a D-glucose. So again it is 6 carbon atom, 1, 2, 3, 4, 5, 6 carbon atom. So what are the carbon atom asymmetric? This is asymmetric, asymmetric, asymmetric and asymmetric. 4 asymmetric carbon atoms. So automatically, so this is 4. Right, kindly follow me. So this is one of the 16 isomer possible. So now what you have to consider, the lowermost asymmetric carbon atom I have to consider. If there is a lowermost asymmetric carbon atom, now just see the more electronegative group along with the atom O is on the right hand side. That's why we are calling it as D-glucose. Kindly follow. So what we are seeing structure is D-glucose. The corresponding mirror image will be L-glucose because OH automatically will come this side. So all other structures are same. In that case, mirror image, this will be L-glucose. So that means D is the same way by changing of H and OH different positions, we can write 16 possible isomer. So D-glucose is one among them because according to the system of configuration, the lowermost asymmetric carbon atom, OH on the right hand side we are calling it as D. So this is we are calling it as D-glucose. This is the most. So by using a D and L system, writing the configurations, we are naming the compound by common name we are giving so far. But we have one problem. Because, let me explain now. What is the disadvantages in this problem? Let me explain this system, D&L system. However, the above system of nomenclature based on fixed projection formula has certain disadvantages. However, the above system of nomenclature based on fixed projection formula has certain, because we are applying a number of enormous compounds, we are writing common name D and L configuration. If you refer literature, a number of compounds will be given D and L with the name all optically active compound. But it is having disadvantages. This system fails when applied to mesotartric acid. So when you apply for mesotartric acid, this system fails. Let me explain what way it fails. Let me take now tartaric acid. So now tartaric acid formula I have already written, that is COOH, CHOH, CHOH, COOH. And if you write all the 4 possible structures, here I have written structure 1, 2, 3. Structure 1, structure 2, structure 3 and structure. There are 4 possible structures. I have already discussed under the optical isomerism. There are 4 possible. Among these, 1 and 2 are called meso, 3 and 4 are called active. Kindly follow. Why it is meso, we have already explained, because there is a plane of symmetry there. One will rotate clockwise, another will rotate anti-clockwise, so both is cancelling, so net effect is 0. That is mesotartric acid is optically inactive. Same thing here also, inactive. So these both cases, that is structure 1, structure 2, they are optically inactive. That is mesotartric acid optically inactive. But go for the configuration D or L, will specify. Just consider the lowermost asymmetry. The lowermost of structure 1, O is on the right hand side, so we have to write as D tartaric acid, D. Go for structure 2, it is a mirror image, automatically it is called as L, the configuration L. So among the meso structure 1, so structure 1 is D, structure 2 is L. And we go for the below, active, there are 2 active of the tartaric acid. Structure 3, again consider lowermost asymmetry. Again, OH on the right hand side. So this is again D. Structure 3 also D tartaric acid. And if you consider 4, this is again L tartaric acid. Now we have confusion. That means when you say D tartaric acid, so D may be active, may be meso. So we cannot use simply D. If you use simply D means next question arises whether it is D means mesotartric acid and D means active tartaric acid, optically active. So the problem started. So that's why in mesotartric acid, this system D and L system of configuration fails. Kindly follow. So in order to overcome this problem, another system of configuration was introduced that is called R&S system of configuration. This is the most important. R&S system of configuration introduced by 3 scientists, Kahn, Ingold and Prelog. So it's also known as Kahn, Ingold and Prelog system of configuration. This is the most important normally question will be asked because they will give the structures and you will be asked to predict if it's an R configuration or S configuration. So kindly listen me, I will go slow in detail. So to overcome the problem, the main aim is to overcome the problem of using DNL configuration. A newer and more systematic method of specifying absolute configuration was introduced by 3 scientists, Kahn, Ingold, Prelog. Kahn, Ingold and Prelog. And this system is called R&S system of configuration. So both way we can name this. R and S system of configuration we can name, or Kahn, Ingold and Prelog system of configuration also we can name. Both way it is indicating the same. Okay, let me give the in detail. So this R and S system of configuration consists of certain rules. And the rules I can classify into 2 types. One is A, sequence rule or priority rule. Another is conversion rule or chirality rule. The main aim is, so we have to specify the configuration, because why we now have to specify? When you want to give IUP as a name, we have to give. I have already pointed out, in the case of, that is the compounds having the, one of the structure is glucose, among their C6H12O6, I informed you 16 possible isomers. All the among the 16 isomers, if you want to give configuration, simply if you use D or L, we cannot give IUPAC. So that we need R&S system. So for that only we are taking the help of R&S system of configuration. So as I have already pointed out, it consists of 2 sub-rules. One is sequence rule or priority rule, another is conversion rule or chirality rule. Let me go one by one. First let me discuss what is sequence rule. Sequence rule or priority rule now consists of a number of rules again. Number 1, rule 1 under this sequence rule. Arrange the atom or groups present in asymmetric carbon atom in the order of decreasing atomic number. So you take any optical acting compound, identify the asymmetric carbon atom. In the asymmetric carbon atom, there will be 4 different atom or groups will be present. Then, based on atomic number, we have to arrange as A, B, C and D or 1, 2, 3 and 4. According to the sequence rule given below. So that is based on the atomic, that is the decrease of atomic number. So number 1 means the atom or group having highest atomic number will be given as A or number 1. The next atomic number B or 2. The next C or 3 and the lowermost D or 4. So the atom having highest atomic number 1, the lowest atomic number 4. So this is the way we have to give number. So we have to arrange the atom or groups according to that. Okay. So now there are a number of problems when we are giving this number, priority order 1, 2, 3, 4 or A, B, C, D. We have so many problems. Let me discuss. One of the problems here. When 2 or more groups have identical first atom, then attached to asymmetric carbon atom, then the priority order is determined by considering the atomic numbers of second and third atom, so on until the priority order is fixed. So if all the 4 different, no problem, we can simply assign 1, 2, 3 and 4. But any 2 atoms are identical, the problem started. So specific example here it is given. So this is a compound having 4 different. So according to this priority, the rule again, priority rule. So this group is given number 1 priority because oxygen is having highest atomic number. The next takes again carbon here is again carbon, here is hydrogen. So first priority, there is no problem, no ambiguity. So we are assigning priority number 1 for OH group. So the oxygen is having highest atomic number. Okay. The next comes carbon. So CH3 carbon is there, CH2 OH is also carbon there. Now which is number 2? So in that case, if you write carbon and methyl group, I can write like this. For a CH2OH group, I can write like this. So carbon identical means the next atoms, that is the rule says, consider second atom, consider third atom, and so on until the order is fixed. So if you take carbon, CH3 carbon, CH2OH carbon identical. The next one hydrogen CH3 and again CH2OH again hydrogen. So okay, equal. The next one another hydrogen in this methyl group and the another hydrogen in CH2OH group identical. Now the third hydrogen in CH3 whereas OH group in CH2OH. So now OH group takes priority over hydrogen. So automatically number 2 is CH2OH. So OH is number 1, CH2O is number 2 and CH3 number 3 and the last lowest atomic number hydrogen is number 4. So this is the way we have to give priority order. Okay, still they have problem. Let me go some rules. Now, suppose when we are giving the priority order, a double bond or triple bond is present, we have problem. How to consider? See here. Suppose a double bond is present, so we have to write like this. We have to imagine like this. C connected to carbon and C connected to carbon separately. The same way, C triple bond C will be considered equal to C again. C again C connected to 3 different carbon atoms. So automatically when you consider C double bond C and C triple bond C, automatically now C triple bond takes priority 3 carbon atom, there is only 2. So this is the way we have to imagine and compare. The next one. So specific example I want to give here to indicate that point. So as usual I am giving the same example. This is glyceraldehyde. D-glyceraldehyde. This is the D-glyceraldehyde. We have seen already the structure. D-glyceraldehyde. Now, just see, this is the D-glyceraldehyde. On your left H, on your right OH, top CH2O and bottom is CH2OH. This is D-glyceraldehyde. So now automatically for H, OH, CH2OH, CH2O, 4 different atoms or groups are there. So it's an optically active. This is the optical active center is there. Okay, now as usual, number 1 automatically priority. So now automatically CHO and CH2OH, that is carbon. How to consider? So I am writing now. CHO should be written as, because C connected to double bond and H. So automatically C double bond should be connected as CO and H3. Whereas CH2O should be written as H, OH and H. So how priority? Whether CH2O takes priority or CH2OH takes priority. You consider one by one. First case hydrogen. So there is hydrogen equal. Second case OH. There is again oxygen, okay, identical. And third case H, but here it is OH. So automatically when you compare to CH2OH, CHO takes priority. So automatically the number 2 will be CHO. Then third will be CH2OH and fourth will be hydrogen. So this is the way, whenever there is a double bond or triple bond, we have to consider as a different way and write the structure like this. Then we have to give priority order. So in this case, this is a clear example to overcome the problem. The next one. So here another problem arises. Just see here. Higher atomic, kindly follow. Higher atomic mass precedes lower atomic mass. The specific example here we can think of. That is, just consider here an asymmetric carbon atom. That is center is C. So 4 different atoms are there. That is here OH group, D, deuterium, tritium and protium. 3 different atoms. So as if you want to consider the priority order number 1, 2, 3, 4. So 1 automatically there is no problem. OH is number 1. OH is number 1 is the no problem. But the number 2, so protium, proton, deuterium and tritium all are having same atomic number. When they are same atomic number, then we have to give priority for mass, atomic mass. And among the atomic mass, so tritium having the corresponding 3 atomic mass, deuterium 2 and protium 1. So automatically now the tritium takes priority. That will we have to give number 2 and deuterium automatically takes the next priority 3 and the lowest is hydrogen. That means higher atomic mass precedes lower atomic mass. This is the most important. So whenever if the same atom is present having same atomic number, automatically the mass number you have to come back and you have to give we have to give the priority. The next one. Now there are problem again. Suppose in groups, when there are two different groups, one is cis group, another is trans group, then cis group takes priority, precedes the trans group. Cis takes priority over trans. What is that? Suppose, let us assume this way. This is an asymmetric carbon. So there is one, that is number 1, this is number 2. And two different, we have given number. Suppose cis is present in cis here, here it is trans, the groups are attached. Let us assume these groups are attached. 1 and 2, some different groups are there. Or if you want to even give, that is one is OH, second some other group. Then third, we have to give priority. Whether it is cis or trans, the same group is attached. When one is in cis form, another in trans form, the rule says give priority for cis. That means 3, trans will be 4. So cis group precedes trans group. This is the way we have to follow. Okay, next one. The same way. Another important thing, Z group precedes E group. Again, we are going to see the next class. We are going to see Z and E notation we will be discussing, and that is coming under the geometrical isomerism. When you are giving geometrical isomerism, cis and trans we will be discussing. There, instead of when cis and trans isomerism is not possible, we will assign based on Z and E notation. Suppose again, as in the case in an asymmetric carbon atom, let me say this is number 1, this is number 2, then next is number 3, and one is Z, another is E group. This group, Z group here, E group here, if it is attached. So 1 and 2 already fixed based on the atomic number. Then for which case we have to give priority? Z we have to give priority or E? The rule says clearly Z group takes priority over E group. So automatically this will be 3, this will be 4, we have to give priority. This is the most important information. The same way, the next one. Now, R group precedes S group, then R takes priority over S. Kindly follow. So we have not yet finalized how to assign R, how to assign S. That is, assume we have, if you have assigned R and S, and the another, again the third and fourth positions, if it is, we have to assign R or S, the problem is, let me give an example. Suppose you take an optical active center, this we have assigned, this is 1, this is 2. So one is, there is an optical active center is R, the same group here it is in S group. Now the question arises. The third order, priority order should be given to R or S. The rule says R takes priority. So I will give 3 for R, 4 for S. That means R group precedes S group. This is the most important. So when you want to assign R or S configuration in this particular carbon containing more than one asymmetry is present. So in the particular carbon I want to specify R or S. So number 1 is fixed, number 2 is fixed based on atomic number. And 3 and 4 it is not yet fixed, means if 3 is R and 4 is S, I will give priority 3 for R and 4 for S. Then I will go for R or S configuration. The same way. Now R and SS group precede RS and SR groups. The same thing. But when? Just now have fixed, same way. Suppose let me say this is 1, this is 2. One side is RR, another side it is RS or SR. If it is present, R or S. So automatically that R or S group will take priority number 3. This is number 4. This is the rule says. So if you are comparing one side RR, other side RS, kindly follow all the atom groups are identical. We cannot give based on the atomic number, we cannot give priority. But in that case, the rule says very clearly RR or SS group precedes RS or SR. That means RR or SS takes priority over RS and SR groups. This is the most important information. Okay, kindly follow. Now, once kindly follow that number 1, that is priority we have given. So, based on atomic number, we have to give priority 1, 2, 3 and 4. So, whenever any problem is there, I have discussed subrules, how to overcome the problem. I have already discussed. Okay, let us assume, by overcoming all the problem, we have assigned priority order 1, 2, 3 and 4. What is the next step? Now we have to assign R or S. What is the method? That is called the conversion rule. So based on this priority order, we have to predict whether it is R or S. That is the rule here. Now just see, once the priority order of atoms or group is settled, we have discussed just now, The configurational assignment is made by applying the chirality rule or conversion rule. What the rule says? Now, in case of three-dimensional model, the molecule should be viewed from the side remote from D or 4, fourth priority. That is the lowest priority. So, if you are having a model, view the model in such a way that fourth priority should be away from you. So, kindly, this is the most important. And now I am having the model D-glyceraldehyde. Just see here. This is the D-glyceraldehyde. So, on your, that is D-glyceraldehyde. Now, kindly follow. Okay. Now, just see, this is on your that is what's on your right, this is on your left, below CH2OH, above is CHO. This is the glyceraldehyde, D-glyceraldehyde. Now, so now we want to fix this that is the configuration. So what the rule says, among these, what is the lowest priority? This is the lowest priority. So what is OH number 1, CHO number 2, CH2OH number 3, H number 4. So kindly follow. Now what we are doing that, let me say here again. CHO, H, OH and CH2OH. This is the D-glyceraldehyde. On your left H, on your right OH, above CHO, bottom is CH2OH. So that is we are viewing here a model. Now, so the rule says the lowest priority among these, H is the lowest priority. Keep the lowest priority. And the rule says, then, now it is, if A, what is A or 1? A, number 1, B and C. Kindly follow. Keeping the lowest priority away, A, B and C. 1, 2, 3. Arrow moves. If the right-handed turn, clockwise turn, configuration is on. Kindly follow. So with the model I am giving now. 1, that is A, B, C, fourth priority here, D is here, or 1, 2, 3. If it is clockwise rotation, clockwise, it is assigned on. Suppose if A, B and C trace the left-handed turn, then the configuration is yes. So I have to check you again, same information I will give now. So now, can you see this is the L-glyceraldehyde. OH is on your left side. OH is on your left side. This is L-glyceraldehyde. So automatically lowest priority, you keep the lowest priority. So number 1 OH, number 2 CHO, number 3 CH2OH. That is A, B, C or 1, 2, 3 anti-clockwise. Anti-clockwise means again it is S configuration. S configuration. So kindly see, if A, B and C now takes a right-handed turn clockwise, the configurations are R stands for rectus, a Latin word meaning right. The same way, if A, B and C now traces a left-handed turn that is anti-clockwise, then configuration is S, where S stands for sinister, a Latin word meaning left. This is the most important information. So with the model it is easy. Now, just see this is board, that is in board. I have shown you model. Now in the model, three-dimensional model, we are saying A, B and C, this is clockwise or this is anti-clockwise, yes. This is the way we have to draw arrow. So with the model it is easy, but in two-dimensional Fisher projection how to draw, that is the most important. So now I can going to give idea for two-dimensional with the help of Fisher projection how to predict RRS configuration. So here I am showing 4 different groups A, B, C, D. So what we have to do? Neglecting the fourth priority, draw arrow connecting A, B and C or 1, 2 and 3 in the two-dimensional cross. So you just predict, you draw the structure, predict the priority 1, 2, 3 and 4. Now fourth priority, neglect the fourth priority, draw arrow. So this is the fourth, this is ABC, arrow moving clockwise. If arrow moves clockwise, configurations are. If the arrow moves anti-clockwise, the configuration is yes. If the arrow moves in this direction, it will be yes. So this is R, this will be S. This is again for in Fisher, so this is the way we have to follow. Let me explain with a suitable example. Now, so when we are giving that one problem arise, what we think? That is, so when we are giving, we are going to draw arrow. Arrow moves clockwise, neglecting the fourth priority, we are going to draw 1, 2, 3. If arrow moves clockwise, R. If arrow moves anti-clockwise, yes. Suppose, problem will be there. What way? Because identify the position of the fourth priority to overcome the problem. If the fourth priority occupies vertical position, then predicted configuration is correct. This is the most important. So this is for two-dimensional notebook and board. If the fourth priority occupies vertical position, top or bottom, whatever you are predicting into board and notebook is correct, or R is correct. Suppose if the fourth priority occupies horizontal position, either left or right side, the configuration that you have predicted is opposite. That means the configuration is opposite of the predicted. Whatever you predict, the real will be reverse. This is the most important information. Let me explain with the suitable. Kindly follow me. D-glyceraldehyde. This is another example. Just see here again. This is the D-glyceraldehyde. On your right is OH, on your left is H. So this is CHO, CH2. This is D-glyceraldehyde. And keep the lowest priority away. Now, number 1, OH. Number 2, CHO. Number 3, CH2. Clockwise, it is R. So D-glyceraldehyde is R, L-glyceraldehyde is S. Okay, now just see here, that is model. Now we come for the two-dimensional board. We know we have already priority, we know OH number 1, CHO number 2, CH2 is number 3. So now we have to connect, neglect the fourth priority, draw arrow now. 1, 2 and 3, this is the, let me show the arrow. 1, 2, 3, this is the arrow anti-clockwise. So anti-clockwise means yes. But the fourth priority occupies in the horizontal, the reverse is true, that is R is correct. S is not correct. Because when the fourth priority occupied either left or right, then automatically the reverse is the correct from the predictor. I mean, if you predict S, the correct is R. If you predict R, the correct is S. So this is the most important information. Okay, now in order to understand this, information, I will show you 12 possible structural representation for glyceraldehyde. So for glyceraldehyde, this is a D-glyceraldehyde, kindly follow me. D-glyceraldehyde, we have discussed already R. Just kindly look at me. This is the D-glyceraldehyde. On your right OH, on your left H, that you have seen on the board. This is. So as per the rule, if I am keeping the lowest priority, this is for viewing the model. Model is easy, but unfortunately when you go for examination or class, then we cannot predict if the model will not be allowed to carry. So in that case, the easy method is you keep the lowest priority away, number 1, number 2, number 3, this is R. So D-glyceraldehyde is R. Okay, now what I can do is, so the same model I can view in 12 possible representation. What way? Just see, let me show you now what are the 12 possibility. One is, I will keep OH above. Kindly follow, this is the OH above. By keeping OH above, kindly follow the molecule model is R configuration. You see, D-glyceraldehyde we have predicted with the model it is R. But how come when you are viewing the structure, how many possibilities? Just see. I am keeping the OH. Now this is one configuration. That is on your right H, on your left CHO, CHO. Now another configuration. Just see. This is second. Now this is the third one. This is the third possibility. So there are 3 possibilities by keeping OH. See the board now. The possibility here it is, the correspondingly this is 1. The fourth period is here. So number 1, number 2, number 3. I am not worrying about the fourth priority. So the configuration is R. Because I am not worrying about the 4. The arrow moves clockwise, it is R configuration as per the rule, the fourth priority vertical. The same way look at the structure 2. 1, this is 2, this is 3. So this is moving anti-clockwise, so it should be yes, but the fourth priority is the horizontal, so real will be R. The same way, now go for in this structure, so number 1, number 2, number 3, it is moving Anti-clockwise, again, fourth priority occupies. So as per the rule, yes, so original should be R. In all the three cases, when you are keeping OH at the top, three possible structure we are writing, all the three are R, but we are getting confused here. Kindly follow. In this case, we are writing as R, but that is, sorry, this is OH, CHO, CH2OH, it is yes. If you predict it is yes, but actually it is R because here is horizontal. So the very clear. Fourth priority occupies vertical or horizontal reverse. In both cases, sector 2 and 3, it is an horizontal, so reverse is true. The same way. Now, by keeping CHO at the top, I can write three possible structure. And again, as per the rule, I can predict the configuration. Just see. Number 1, 2, 3. This, as per this, the anti-clockwise, it is yes. But the fourth priority occupies at the horizontal, so real will be R. Same way, structure 5. Now, number 1, number 2, number 3. So it is again anti-clockwise. So that is predicted is yes. But the fourth priority occupies, that is the horizontal, so real will be R. The same way, come for the structure 6. This is number 1, 2, 3. This is moving clockwise, so real is R. That is fourth priority occupies vertical, so original predictor now the real also R. So this is the way we have to predict the configuration. Let me go to the next possibility. So by keeping CS2O at the top of the Tata model, so now we can draw three possible structures as usual. Number 1, number 2, number 3. So predictor configuration is yes, but the fourth priority in the horizontal, so it is real is R. The same way, sector 8, again CHO top. This is 1, 2, 3. So it is clockwise R. Fourth priority vertical. So this is real is also R. Then sector 9, 1, 2, 3. This is anti-clockwise S configuration. Fourth priority occupies at the horizontal. So real will be R. In all the cases, R configuration. It is obeying the law. Okay. The next possibility. Now I am keeping now hydrogen at the top of the model. I can now draw three possible structures. This is the most important because in the examination you will be getting confusion. So kindly avoid that confusion. I am giving the guideline. So by keeping hydrogen at the three possibility, any sector can be given. So let me repeat again. So as per the rule, 1, 2, 3. It is moving clockwise. So that is predicted configuration R. Fourth priority of at top. So real is also R. Coming for structure 11. That is 1, 2, 3 again. So all the structure, that is, it is clockwise R. So fourth priority occupies vertical, real is also R. Then structure 12, 1, 2, 3 again R. Fourth priority again H. So real is also R. In this case, wherever fourth priority occupies top and bottom, the real and predictor will be same. So this is the most important information regarding for RS configuration. Just kindly remember, let me conclude now. That is, when you are predicting the configuration R or S, now give based on the atomic number, give priority 1, 2, 3 and 4. Once the priority order is fixed, now draw the structure, view the structure and draw the arrow neglecting the fourth priority. If the arrow moves clockwise, 1, 2, 3, assign R. If the arrow moves anti-clockwise, assign S. And now during this, if the fourth priority occupies vertical positions, predicted and real are same. If the fourth priority occupies horizontal positions, so predicted will be the reverse of original. So you should be very careful when you are analyzing. So I will take one more example before concluding. That is, this is the D-tartaric acid and L-tartaric acid. Now the same, because when you are giving, that we have already come across, the problem started only with the D and L tartaric acid and mesotartaric acid. That's why we have not following D and L configuration. That's why we introduced R and S configuration. So how to name IUPAC? Just see here. So here I am giving a D tartaric acid. I am giving IUPAC name as. So for this is number 1, this is number 2, the entire group number 3. So 1, 2, 3 clockwise. It should be R. But the fourth priority horizontal. So it should be S. The second carbon atom yes. The same way. And if you consider here, this is 1, this is 2, again, the entire group 3. So clockwise R, again, fourth priority occupies horizontal yes. So both cases yes, just see here. So when you are giving the name for IUPAC name for D-tartaric acid, you have to name it as 2S, 3S, dihydroxybutane, 1,4 dioic acid. This is the most important information for conversion. So without R and S configuration, we cannot give IUPAC name for tartaric acid. Same way. Now let me go for L-tartaric acid. Again same way. This is number 1, COH number 2, this entire group 3. This is anti-clockwise, yes, but fourth priority occupies the left, so it should be R configuration. Same way, 1, 2 and 3, this also yes, but really is R because fourth priority again on the horizontal. So in both cases RR, that's why the name, IUPAC name is given as 2R, 3R, dihydroxybutane, 1,4 dioic acid. This is the way we have to give the R or S configuration. Only if you assign R or the S configuration, then only you can able to give IUPAC, systematic IUPAC name for any optical active compound. Otherwise, it's not at all possible. The final, I will conclude with this example. D-glucose, we know we have to come across already, is a optical active compound containing 4 asymmetric center. So the same systematic way if you follow, the glucose can be named by IUPAC name as, so there are 4 asymmetric center, second carbon atom is assigned as R, third carbon atom is assigned as S, fourth carbon atom is assigned as R, and fifth carbon atom is assigned as following the same rule. And then we can give IUPAC as 2R, 3S, 4R, 5R, 6 without the optical center, pentahydroxyxN1R. This is the correct IUPAC name for D-glucose. So any optical active compound, we can give systematically IUPAC name based on this R and S configuration. I hope you have enjoyed the lecture. Thank you.